Let's finish this thing up with a discussion of polymers. Let's see. Let me check one more thing. Okay, that's good. All right, polymers. We're roughly going to divide this chapter up into five sections. The last one, biological polymers, it depends. We may go into it in detail because if you're going to go into biochemistry or any medical profession, you're going to get hit with polymers in biochemistry, biological polymers for sure. So let's jump on our horse and ride. So at the very simplest understanding of polymers, they are very large molecules that are constructed from very small molecules. That's where the poly comes from. Lots of small molecules hooked together to make one big molecule. And usually, in fact, I can't think of a single example where you can't identify a repeating unit in the polymer. It may be a very small unit, it may be a little bit bigger, but there's always seems to be a repeating unit, and that's by design. If you're studying natural or biological polymers, then it may take some, you may have to work at it to find out what the repeating unit is. And that's been a test of science for several decades. But if you're an synthetic organic chemist, then you design the molecule from the start with the small molecule, the repeating unit in mind. Sometimes polymers are called plastics. And I'm not sure where that name came from. Maybe it's probably from the Latin, which means malleable. So it's more a functional name than it is a definition. We see plastics everywhere. Polymers are everywhere. In fact, there was a time when everything that we had around us was constructed from natural products. I mean, we may take the natural products and engineer them, like most recently plywood or oriented strand board, right? They start off as natural polymers, cellulose, and we engineer them to be something that we want. It's only in the 20th century that we've come to the point where we engineer at the molecular level and produce. And you look around you, and if it's not metal and you can't see that it's wood, then it's probably a polymer. It's probably plastic of some kind, or maybe ceramics. I have to give ceramics their due. So we see polymers in drinking bottles, storage containers. We even plumb our houses with plastic now, where it used to be iron pipes that were packed with lead fibers. Our tires on our automobiles, the first tires were made with natural rubber, and they didn't last very long. It wasn't until let's see, I don't want to speak out of turn. I think it was Goodrich who discovered vulcanization, and that stabilized the polymer, the natural rubber, and later other polymers. And we're going to talk about that later. It's called cross-linking, to make the polymer tougher so it would stand up to 60, 70, 80,000 miles of wear on the road. Plexiglass, right? Plexiglass is everywhere. And its close cousin, Lexan, or polycarbonate. In fact, the lenses on my glasses are made of Lexan or polycarbonate. Teflon, right? We even cook with Teflon. Kevlar. Kevlar, you'll find that many places, but one that's most popular, most recognizable is Kevlar in bulletproof vests. All right, somebody had to invent these things. All right, there are various ways, various mechanisms that will produce polymers, and they're chosen for various reasons, right? Maybe you're restricted by uh, the monomer, the starting material, the small molecule. It will only polymerize a certain way, or you prefer to polymerize it a certain way because it's faster at milder temperatures, milder conditions. But for whatever reason, we have these different methods of polymerization in our toolbox. Polystyrene is one example. And this one is polymerized by what we call radical polymerization. Remember what a radical is. It's any atom or molecule that has an unpaired electron, which makes it extremely reactive. A lot of these polymers were discovered by accident. Polystyrene is one of them. And anytime you have these packing peanuts or packing morsels in a box, those are probably polystyrene. Sometimes we use polystyrene to insulate the walls of our houses or our mobile homes or recreational vehicles. So what's required is a monomer, the simple molecule that you start with. That's the monomer. And when it's linked to other monomers, then it forms this long chain. So how do you get it to do that? One of the ways is with free radical polymerization. Now, only part of this polystyrene is shown. It's a much, much bigger molecule. And that's one of the unique things about polymer chemistry is that it's more of a, I thought organic chemistry was kind of a kitchen chemistry. In other words, you had a recipe and it worked, so you went with it. And then we try to figure out why it worked on the side. Whereas with classical chemistry now, you generally go in and you know the conditions that you want to begin with, and you can go from the beginning and start with conditions and end up with what you expect. Whereas organic chemistry traditionally has been more like you end up with something and then you go back and figure out how it got there. So ideally, you can repeat the process later. Now, it's advanced some over the years, and we know a little more about how these reactions occur, but polymer chemistry is at the stage where we do understand much about what happens, but it's still as much an art as it is a science, building the polymers. And we start with a monomer, and then we got to figure out how to connect one monomer to the other. And we know about these various types of reactions, right? The nucleophilics and the electrophilics and additions and eliminations and all those different types of mechanisms. And they can fit into various types of polymerization mechanisms. The big difference between polymerization and what we've learned up to this point is that those reactions are self-repeating, right? They just keep going on and on and on. So we have a sequence of events that we try to control. So we start with a monomer, and let's see. Let's get some definitions out of the way. The type of monomer we're dealing with here is a vinyl. Is a vinyl polymer. The vinyl group is double bonded carbon. And we'll go back here. Notice that there's the double bonded carbon, and this is the vinyl group is attached to a benzene group, and that makes it styrene. Or vinyl benzene is styrene. Now, any non-hydrogen atoms that are attached to the main chain of the polymer, they can either be called side groups or pendant groups. Pendant referring to just hanging off the sides. And the physical and chemical properties of the polymer can be modified by ending up with a polymer with various types of side groups. That's one of the reasons that Kevlar is so tough, because Kevlar has all these benzene groups sticking out on the side, makes it very difficult to penetrate, especially if you pack them close together, as they do in bulletproof vests. I should say bullet-resistant vests. Okay. So here we have the pendant groups in the polymer now are derived from the monomer, and the pendant groups are these benzene rings as attached to the main chain. The main chain can be followed atom to atom all the way from one end to the other. You don't have to go off, and in fact, if you deviate, you're onto a side group. A side group is kind of like a dead end. Okay, this is the way we write in a condensed form the polymer. We figure out what is the repeating unit, right? In this case, it's two carbons with single bonds, carbons, attached with a benzene group, and then there are two sigma bonds off to either side, and that means on either side you get another repeating unit. So we enclose them in brackets. We show that the extensions are beyond the brackets or parentheses, and then we subscript it with an n. Now, if we leave the n as a variable, then we're saying that it could be any length. But if we have an idea of how long the polymer is in terms of repeating units, then we'll put a number there for n, and that will designate just how many there are. There's another expression here that's useful for polymer chemists. It's called the degree of polymerization. And that's what the n means. The n is the degree of polymerization. And it can be several dozen, it can be thousands, it can be hundreds of thousands. Some of these polymers are massive. Now, when you get into biochemistry, they'll be using a different unit of expressing the size of those biological molecules. They're called Dalton units. So set that aside for later. If you're going to take biochemistry, then you'll run into that again. Now, these molecules still have molar masses. Right? Don't get me wrong. They can still be expressed as grams per mole. It's just that it's difficult to control a polymerization reaction where you get molecules that are all exactly uniform size. There are so many variables, and the polymerization reaction occurs sometimes so rapidly that the best you can do is get a range of sizes. Now, if we do have an idea of what size the molecule is in terms of its molar mass, and we also know the molar mass of the repeating unit, Then we can create a ratio between those two. The molar mass of the polymer and the molar mass of the repeating unit. The ratio there will give you the degree of polymerization, or the value for N. And there are various techniques that polymer chemists use to evaluate their polymers in terms of their molar masses. I mean, in general chemistry, we learned various techniques for determining the molar mass. Colligative properties is one of them. But there's very specialized techniques that polymer chemists have to use in order to estimate the molar mass of the polymer. Okay. Now, I want to draw a distinction between the monomer and the repeating unit. The monomer is the small unit, the small molecule that is used to be polymerized. And then the repeating unit is after the polymer is formed, you assess the polymer for its repetitive nature, and then you look for the repeating unit. They'll be related. Notice that the difference between styrene and polystyrene in terms of its repeating unit is the absence of the double bond. Styrene has a double bond carbons, and polystyrene does not. And that also gives you a clue as to how the polymerization progressed. In other words, the double bond gave up those electrons, and they formed a bond between that monomer and the next monomer, or the end of the polymer. So here's an example. Notice we have carbon with two hydrogens, then it's bound to a carbon with a hydrogen and a chlorine. And then another H2, and then a CHCl, and then a CH2. And so we can assess this for the repeating unit. And it should be something like this. Notice if we break these bonds at those squiggles, just to the right of each chlorine, then we can set up a repeating unit here like that. And then the degree of polymerization depends on reaction conditions, really. Now, can we assess what was required? What was the monomer that was required to make this polymer? We can speculate, and vinyl chloride would be a good choice, because notice that if we break a bond, where are we going to put those electrons? Right? If we're trying to describe the polymer, then of course we leave them intact and we just say they extend to the next repeating units. But if we want to assess them in terms of the monomer, then we say, where do those two electrons go? One on either side, go into the middle, make a double bond. So that's where we get the vinyl chloride as the monomer. And everybody knows polyvinyl chloride, PVC, right? We make water pipes, sewer pipes, all kinds of stuff out of that particular polymer. Now, we'll also say that making the polymer, say, on a massive scale, like polyvinyl chloride is made tons and tons a year. Then what do you do with it? Well, usually when these polymers are produced by a manufacturer, let's see, I think Baton Rouge had one at the Exxon plant. They produced polymers when I lived there. I don't know what they do now. But they usually produce the polymer in a form that's transportable. Maybe they pelletize it, or little granules or something, and then they can put it in containers on rail cars or on trucks, ship it off to some whatever plant needs them, and then they engineer it further from there to make the final product. So, and you can modify the physical and chemical characteristics of a polymer by changing, particularly you can change the side groups, or you can put it under pressure, or you can mold it. And those various actions that you conduct as a final producer will change slightly, but will engineer the characteristics of the final product. So just producing the polymer is not the end of the story. That's what I'm trying to say. Okay, back to the topic of radical polymerization. So if you're going to polymerize this polystyrene, you need a way to get it started. You need an initiator. So this is the first step. After you have your ingredients identified, then this is the first step is initiation. How do you get the thing started? Right? And there are various ways to introduce free radicals into a mixture that will kickstart a polymerization reaction. One of those that's commonly used is benzoyl peroxide. Right? It has a benzene ring on this side like that, and it has a benzene ring over here like this, and then it goes like this, and like this, like that, like that. Okay, so you've got these. Here's the peroxide, right? And benzoic acid would be this with a hydrogen. Instead, we take it and make a peroxide out of it. Now, this bond right here is very weak. And since the molecule is symmetrical, it's got the same groups this way as this way, then it's more likely that the bond, rather than be heterolysis, breaking and going this direction, it's homolysis. In other words, it'll break right in the middle, and one electron will go this way, and one electron will go this way. No, excuse me. I think it goes this way. There we go. And that would be 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yeah, that would it. That would do it. So we produce 2 free radicals from this process in order to get to initiate the reaction. So there we see in the middle the benzoyl oxyl, that's a mouthful, radical. But this is not stable. It's very unstable. And in order to stabilize it, that free electron, well, a bond is broken. Let's put it that way. A bond is broken here. And we get like this, like that. And the free radical electron from here and free radical electron there get together and form another double bond. And this bond breaks and produces carbon dioxide. So that part of the molecule goes here. This part of the molecule goes here, like that. And this is the phenyl radical is the initiator. All right, so it's a 2-step process to get to that point. Now, how do we get it to do that? Well, there are 2 ways. Since the bond is very weak for benzoyl peroxide, we could just increase the temperature, and it will break the bonds. And it doesn't take much to get things started. Or you can do like the dentist does when they do a reconstruction on a tooth. They build up the the goop that they put on your tooth to cap it, rather than using a, if it's a small defect, then this works very well. Right? If it's a big defect where they have to, they'll send off and get a zircon cap and put that in there. But if they use this polymer that they put in to replace parts of your tooth, notice that they'll have this device with ultraviolet light, and you'll have your glasses on, they'll have their glasses on, so nobody gets damaged, their retina's damaged, and then they'll shine that light on that goop, which it has built into it benzoyl peroxide. And that light, so they don't have to heat up your whole head just to get it to start, they use ultraviolet light, and it kicks it off. And after a few seconds of initiation, they can back off and let it do its thing. And it will polymerize, it will form a very hard surface that they can then grind down and make it fit with the rest of your teeth. I've had that done several times. Okay, so once you've initiated it with this free radical, then you have propagation. Can't even spell propagation. And this is where the reaction just tends to just kind of roll downhill. It just continues. In other words, we get this free radical that takes one electron from the pi bond and one electron from the radical, and makes a bond with the carbon, and the other electron from that pi bond moves over to the carbon attached to the phenyl group, and that makes another free radical. So now that free radical goes and repeats the process. So you'll have this this end group on your molecule, and then the bigger it gets, the less important that end group becomes. And remember, these single barbed arrows means the movement of one electron. Okay. This is known as chain polymerization. It's a free radical process, a mechanism, but it's a chain polymerization. In other words, the only part of the molecule that reacts is the end. One end of the molecule is available to react, and it just continues to extend the chain. Right? Now, wherever the free radical initiator starts, right, there's going to be more than one of those in the solution. So wherever it starts the reaction, that those are independent chains that continue to grow. This can also, this is semantics or just general characterizations. We can also classify some of these reactions as addition polymerization. The reason we can call them addition is because we don't lose anything. We add something to them, right? Like adding to a double bond, and we don't lose anything. There's no leaving group. So these are addition polymerizations also. Now, if we lose a group, then we can't call it an addition. But I don't know of any polymerizations that do. Well, yeah. There's an example. We'll get to it. Okay, let's see. There we go. So this is an artist's rendition of what a chain growth polymerization looks like. The molecules start in several places, and they just continue to grow. Now, when does it stop? Well, there's initiation, propagation, and then it has to stop sometime. And these steps are the same for any polymerization. We're just using free radical polymerization to introduce these concepts, but it works for any polymerization. You got to get it started. It's going to proceed. It's going to propagate, and then it has to end. Now, sometimes it ends on its own, or sometimes you choose the conditions under which you cause it to stop. Okay. One way that the propagation ends is if two growing polymers just happen to encounter one another's free radicals. So the free radical on this polymer and the free radical end on this polymer, they happen to meet and they form a bond. That stops because now there are no more free radicals. That's known as combination. That's a combination termination. So in our example here, we have combination as a possibility. And the other is disproportionation. Now, you may have seen that in inorganic chemistry, the disproportionation reaction. They're similar concepts, but they're not the same. So we better define our terms here. This is what a combination does, and it stops the growth of the chain. All right, I'm going to move on. Disproportionation, on the other hand, describes a reaction in which two identical species react to produce two different products. In other words, if we get these two free radical ends together, rather than form a single bond between them for combination, we get a transfer. In this case, we get a proton transfer. So a bond, the bond breaks with this hydrogen. One of the electrons is combined with a free radical to attach the hydrogen. That kills that free radical. And then the other electron from that hydrogen bond break goes to make a combination with the free radical on the other molecule, goes to make a double bond. So we get two different ends to the molecule. That's disproportionation. They're not the same. All right. Let's see. So this just emphasizes the difference in the end groups, right? They will both have the same end group from their initiation, but they'll have a different end group from the termination. So what do we say about end groups? When we terminate by combination, then both molecules that stop growing have the same end groups on both ends. Both of them have phenyl groups on the end. All right, I think that's more trouble than it's worth. But with disproportionation, we have different end groups. You know, I think this is repetition that we don't need. Now, with disproportionation, the two molecules could be different sizes for either mechanism, combination or disproportionation. It just depends on how far along one propagated compared to the other. So we can't say anything definitive about combination versus disproportionation in the size of the molecules, I don't think. So I will say this, when we're evaluating the structure of the molecule, we don't consider the end groups. In fact, when we write the uh, uh, reduced form, the abbreviated structure, we leave the end groups off. The end groups aren't even considered. We only consider the repeating units. Simply, I think because the end groups have very little impact on the physical and chemical properties of the polymer. Because there's only one on one end and one on the other, they don't matter. Now, how about regiochemistry? When you have this free radical, and we want to add another monomer to it, we can either add on the symmetrical end or the asymmetrical end of the molecule. So the top one we add on the symmetrical end, the tail versus the head. And in the head-to-head edition, we have actually, I think the second one, the head-to-head, would be less likely. And for one very simple reason, steric hindrance. Because you got that big phenyl group sticking out there, getting in the way. Access to that free radical is simpler and easier on the tail than it is on the head. And this is due to the unsymmetrical monomer. Okay. And let's see if we get anything more out of this. Okay. Steric repulsion, right? I hit the nail on the head for that one. Steric repulsion will cause the second head-to-head addition to be less desirable. In other words, the more likely attack will come on the tail, simply due to steric hindrance. Also, if we do, that's not the only reason. The second reason is what free radical forms from that process. If we do head-to-head, then the free radical has to reside on a primary carbon. Whereas if we do a head-to-tail, then the free radical resides on a secondary carbon that's resonance stabilized with the phenyl group. Right, so it's much more stable. That's why the first one, the head-to-tail addition, is preferred. All right. So, when styrene polymerizes, these sp2 hybridized carbon atoms of the vinyl group become sp3s. Right? sp2s because they have a pi bond. sp3s now because they have 4 bonds to the carbon. They have 3 carbons and 1 hydrogen that's not written. Remember, if you see a carbon here with 3 sigma bonds, nothing else there has to be a hydrogen. Right? We just don't write it. Like this carbon has 2 bonds on it, it has 2 hydrogens. Right? Just like this benzene ring, it should have 1 hydrogen at every carbon except for the one where we're attached as a side group. All right, here's another concept. Tacticity. Tacticity. This is references the pattern or the lack of a pattern of side groups on a molecule. Right? If the molecule is atactic, the side groups are all attached randomly. There's no pattern whatsoever. Um, and this often occurs if you use benzoyl peroxide as an initiator. Isotactic configurations are all the same. That is, they're regular spaced, and the isotactics have, in this case, our example here, the phenyl groups are all pointing toward us. Syndiotactic are alternating. Right? So those are the three possibilities for side group positioning. Now, if we use this Ziegler-Natta catalyst, we can control whether it's isotactic or syndiotactic. If we don't care, then just use benzoyl peroxide. It's probably cheaper anyway. But we're going to talk about that special catalyst here in a second. Okay. I mentioned earlier that it's very difficult. It's not impossible, but it's very difficult to come out with a product, a polymer that, oh, we lost Galen. Probably internet problems. So most often polymer chemists try to characterize their products. There he is. Try to characterize their products with a distribution of polymers. So this is an idea here. If we want to have a degree of polymerization around 1250 in this case, then we know that we need to stop the reaction at 18 minutes or so, around that time. If we just let it continue to run, then we've got another opportunity at about 24 minutes where we can get, well, now that didn't. All right, let me back up. I was headed down the wrong rabbit hole. The goal of most organic synthesis is to produce a single product in high yield. Okay, it's difficult, or sometimes impossible, for chain polymerization mechanisms. Therefore, the lengths of the chains that are produced cannot be precisely controlled. Instead, we have a mixture, a distribution of chain lengths. And we can describe those with an average molar mass. So, for example, commercial grade polystyrene has an average molar mass of 200,000, or let's see, molar mass of 200,000. Oh, I'm sorry. I've misinterpreted this graph. This graph is of this is a chromatograph. Yeah, this is a chromatograph. So if we take a column and we put our mixture of polymers up here, and it has to be soluble, and we have to choose the right stationary phase that will attract, then we and sometimes it's a matter of the stationary phase having holes in it, right? And those small holes will let the small molecules of the polymers go in and come out, go in and come out. So they're delayed. So the longer you go, you're looking at the smaller molecules. The bigger molecules can't get inside those stationary beads, so they just flow right on through. That's why you have the larger molecules coming out first, right? Molar masses here are very high. Degree of polymerization decreases as you go from left to right. Let's see. Here, okay. If I'd let the whole thing run, gel permeation chromatography, which works by size exclusion. Right? So the same concept is true for this gel permeation. The larger molecules don't get into the gel. They stay in the mobile phase and they just move right on through. So the bigger molecules come out first. And we detect those bigger molecules by the millivolts of the signal. All right. So this just illustrates a distribution of different sizes of, in this case, polystyrene. And that's how they're characterized. You know, if you want to produce a product, as a manufacturer, you're making a polymer and you want to market it to some end user who's going to engineer it into some final product, then they need to know the characteristics of that product. You know, what's the distribution of polymer sizes, right? Because our manufacturing process is dependent upon a certain type of beginning product, beginning feedstock. Okay. So now we're going to, this was, let's see, we talked about free radical. Free radical polymerization. And this was chain growth. Okay. Now we're going to look at a different type of polymerization called, excuse me, anionic and cationic polymerization. We'll put those in the same group. Or we could say ionic. Ionic polymerization. And one way is with anionic, and the other way is with cation. So we're going to start with anionic. So we can make polystyrene rather than free radical. We can make it with this anionic polymerization. The initiator in this case is an anion of carbon. Now, how do you get that? Well, one way is to use our alkyl metal compounds, or metal alkyls. Lithium, for instance. If we use butyl lithium, then we're actually looking in terms of the mechanism at the anion, the butyl anion. Okay. Now, this carbon on the end has two hydrogens, carbon on this side, hydrogen on this side, and a lone pair. That's so 1, 2, 3, 4, 5. 6 minus 5 equals, let's see, is that right? On one side. 6 electrons minus 5 electrons. So we have a minus 1. 1, 2, 3, 4, 5. No, that's a plus 1. This is supposed to be a minus. This is supposed to be a minus formal charge. Am I doing that right? All right, so we have 1 here, 1 here, 1 here, 2 hydrogens, carbon. 1, 2, 3, 4, 5. Oh. That's right. I was using all 6. If you're going to do formal charge, how soon we forget. formal charge, you just need to use the valence electrons, right? So how many valence electrons for carbon? Well, 4. How many does it have here? 1, 2, 3, 4, 5. Minus 5 equals minus 1. Okay, they're right and I'm wrong. So that gives this carbon a -1 formal charge, and that makes it a nucleophile, right? It has extra electrons. It's going for a carbon that's deficient. Well, we wouldn't think of that carbon on the end of the vinyl group to be deficient, but it's all relative, right? The double bonded carbon is donating some of that electron density into that pi bond, which makes it slightly deficient. And the negative charge on the carbanion is very, very negative. So it's going to attack that carbon that's out in the open, available. And when it forms that bond with the carbon, that gives carbon 5 bonds, so something's got to give. So the pi bond between the 2 carbons on the vinyl group breaks, and those 2 electrons from the pi bond group go to the carbon, and now we've got another carbanion. So the initiator produces that carbanion, and we can propagate from that point. And it just continues. All right. So how do we terminate? All we have to do is add an acid, right? If we add an acid, then we get a proton transfer to the carbanion, and it stops it. It neutralizes that negative charge. And it leaves us with a conjugate base, right? It leaves us with a conjugate base over here, but that conjugate base can't react, right? It will not propagate. And so we terminate it with an acid. Very simple. Just add that acid, you terminate the process. How about cationic polymerization? Can we do the same thing with polystyrene? Well, as a matter of fact, we can. Just depends on the initiator. So for this initiator, which should have a name, oh, didn't give me a name. All right, let's see. We have this trichloro. Be honest with you, I don't know what to call it. But do we have a positive charge on that oxygen and a negative on the boron? Well, the reason that the boron has become negative rather than positive is because of those chlorines. The chlorines are highly electronegative, and they will draw electron density away from that oxygen through the boron and make the oxygen positive with a positive formal charge. Let's see. Oxygen should be 6, right? And then how many electrons are assigned to that oxygen? 1, 2, 3, 4, 5. So 6 minus 5 is plus 1. Okay, so that oxygen is positive. That makes it an electrophile. And as an electrophile, it initiates by proton transfer. In other words, the proton transfers from the boron compound to the carbon on the vinyl group, the end carbon, using the pi bond electrons. And that makes the carbon that's closest to the phenyl group positive. And from there, once it's initiated, then it propagates from there by cationic polymerization. Now, we know that we can make polystyrene by 3 different methods, right? Free radical, anionic, or cationic polymerization. I wonder if there's a preference, right? Which one works best under certain conditions? Oh, we got to terminate it first. All right, so how do we terminate? We terminate with, let's go back. Notice this molecule that's formed from here still has a negative boron, but now it's got a hydroxyl group on the end. Well, that hydroxyl group, excuse me, that hydroxyl group is here. And this negative boron allows chlorine to be a nucleophile. Well, chlorine is electronegative anyway, so it's going to have its unpaired electrons. So the chlorine then attacks the carbocation and transfers and gives us the neutral boron chlorine compound, and that terminates the reaction. So the end group on this one is going to be chlorine on one end and methyl group on the other end. Okay. Now that doesn't seem like the polymerization is going to go very far, does it? Right? Because you produce the terminator by the initiation step. So we need a way to control that, I think. Now, as a practical application, vinyl polymers tend to be used in anionic polymerization of electron withdrawing groups and cationic and electron donating groups that are attached to the carbon-carbon bond. So our examples down here are for anionic polymerization. We've got this acrolein, which is a propanal. Proper name is propanal. The trivial name is acrolein. And the anionic initiator is going to attack the carbon that's closest to the oxygen because that's the one that's deficient. And then if we want to use a cationic polymerization, we tend to want to form a carbocation that's stable. So this isobutylene, it will form the most stable carbocation attached to the double bond, right? That'll make it a tertiary carbocation, which will be more stable. Okay, ring opening polymerization. Oxyring, for instance, can form what's called polyethylene oxide. The monomer is oxirane, right? And we know from experience that these three-membered rings are highly strained, right? They're very reactive. And this goes through a process of chain growth polymerization. Excuse me. Yeah. It's a chain growth, but it's a subcategory, ring opening polymerization. So what does the mechanism look like? Who knows? It must not be that important. Not for us. I mean, it's important for the industry, but just recognize that that's a possibility. Okay. These reactions are chain growth. These are all chain growth types of reactions right here. Right. Another type is step growth. Step growth reactions occur when molecules everywhere in the mixture have the opportunity to react with other molecules in the mixture because they have the appropriate functional groups. The best example of that is nylon, formation of nylon. And this is a condensation polymerization. In other words, it produces a small molecule as a leaving group or a byproduct. In this case, the small molecule is water. Most condensation polymerizations, most condensation reactions produce water, but they don't have to. They can produce small molecules of any kind. But in this case, we do. We form an amide, right? When we form that bond, nylon, in this case, the most common form is nylon 6,6, which means that you have hexane 1,6-dioic acid or adipic acid combined with hexane 1,6-diamine. And we got amine groups on either end of the molecule. We got carboxylic acid groups on either end of the molecule. So that means these molecules can react on either end. So they are step growth. They can continue to grow anywhere in the mixture. They just have to form the amide bond. Now, what you'll see if you go into biochemistry, you'll see a special kind of amide polymer. It's called a protein. Right? The amide bond is characteristic of proteins, and we call those special bonds are peptide bonds. But in organic chemistry, they're classified as amides. Now they form differently, right? Under the direction of DNA, RNA, and enzymes, special enzymes. So they don't just form, proteins don't just form willy-nilly. Right? They are tightly controlled constructions, polymers. Whereas these are just, they happen at will. All right. There's also, I was looking for another term that's used here. Yeah. Yeah, I may have a slide on it, but now that it's come to me, these are copolymers. A copolymer is formed from usually two different monomers. And each one of those monomers by itself cannot polymerize. In other words, you can't put adipic acid in a mixture and hit it with an initiator and expect it to polymerize. It will not. You can't do it with a diamine either. You can't polymerize that. The only way you can polymerize them is to put them together. So they form a copolymer. Right. Step growth. And this particular example is a condensation. Polymerization. And this just shows you how it can just continue to grow. So once you form a bond, the amide bond between the two molecules, you've got an amine on one end and a carboxylic acid on the other end, and they can react with other molecules and continue to grow. So this is what it would look like, an artist rendition. I don't know if I showed this in my general chemistry class. We have changes of state. In other words, you got two liquids together, and if you put, I forget which one is more dense. Probably the adipic acid is more dense. It's on the bottom. And then you pour the hexane 1,6-diamine on top easily, so it just forms a layer. And then you reach in and you grab something from where they touch one another, you pull it out, and there's your nylon. And then you put it on a spool and you just roll it up like that. And wherever they meet, fresh meat, you get more nylon. Okay, chains continue to grow. Now, here's another copolymer. We have terephthalic acid and ethylene glycol. And we use an acid catalyst. Now, I'm not sure about the mechanism here. Acid catalyst probably makes the alcohol more acidic so that it will react. And here we form an ester, right? We're not forming an amide here. We're forming an ester. See where we have the carboxylic acid group here, and then it's formed from the between an alcohol and a carboxylic acid, you get an ester. So this is a polyester. Polyethylene terephthalate, PET, right? Everybody knows that. Any bottle of pop that you get is probably going to be in a bottle made out of PET. And it'll have this symbol. It'll have the recycling symbol right here. Will be 1. All right. Here's another one. Right. Toluene diisocyanate and ethane 1,2-diol or ethylene glycol. Right. That's the same stuff you put in your radiators, in your automobile radiators, to keep them from boiling over or freezing in the winter. Same stuff, no difference whatsoever. And this is a polyurethane. There's the urethane grouping right there. This is a functional group. And if we write the abbreviated form, the condensed form, then we have to look for the repeating unit, and the repeating unit is big, right? It's over here, it's big like that. Now, what this says is on this end, we've got this oxygen, and that oxygen should be attached to the next neighboring one through this as part of the urethane functional group. All right. So it didn't tell us how we stop the reaction, though. How do we terminate these? I don't know. Maybe we just let it run until it runs out of reactant. Well, that's one possibility. When it runs out of reactant, it stops. So if that's the case, then we control the reaction by the molar combinations. We know how many moles of this one it takes, how many moles of this one it takes. Only put that much together, and you will have some left over, because of experimental error. You can't measure exactly to molar ratios. So you'll end up with, you'll end up with some unused reactants, monomers. But as a practical matter, when you go to manufacture these things, how is nylon manufactured? Right? Well, the machine has a feedstock, one feedstock coming in here, another feedstock coming in here, and right there, under pressure, is the spinnerets, right? And they produce those little fibers of nylon. So we bring them together and push them through that spinneret, and they come out as single fibers. So the reaction takes place right here, and that's it, right? When you get the fiber, there's no more to react. So maybe that's the way they control it. Now, up to this point, we've assumed that the polymers are linear. That is, they form by growth at the ends. But that's not always the case. You can have branching also, branched polymers. Branched polymers occur when there's some place in the molecule that is a reaction site. If that's the case, for instance, with this free radical polymerization, we might be able to take that free radical and attack a hydrogen somewhere in the middle of a neighboring molecule and form a bond. And well, actually, we've transferred a free radical to, okay, this is how the reaction site is produced. So with free radical reactions, we can transfer that free radical from this molecule, which stops its growth, and then it transfers a free radical to the middle of the molecule. And when it does that, it makes the available, that free radical available to react with some other unit, and that forms a branch. Now, there are ways, I'm not privy to exactly how they do it, but controlling reaction conditions, you can minimize the branching. Right? Because, for instance, if you want to produce, everybody's heard of low-density polyethylene and high-density polyethylene. Low-density polyethylene is highly branched, lots of branching, which means the molecules are confused, right? They don't get close together, and that makes them lower density. And it makes them not as strong either. But they do have certain characteristics that are desirable. They're more easily malleable, right? They can be formed. But if you want a high-density polyethylene, you want to minimize branching so that you can get those molecules laying right on top of each other. Right? Individual molecules with no branching can do that, and that increases the interaction between the two. Yeah, I'm going to let it go at that. I think we talk about it a little bit later. Here is the very first polymer, and it's a network polymer. So let's see, 5, network. Well, actually, we talked about branching first, right? Branching. And then networks. So what do we mean by a network? I like to think of a network as, in general chemistry, we talk about network solids. And a perfect example of a network solid is diamond. It branches in every direction, in 4 different directions, and essentially produces a single molecule. In other words, that polymer branches until it gets as big as you want it. And this is also a copolymer. The phenol plus formaldehyde produces this product called bakelite. Bakelite was the first polymer produced. The first, I hesitate using plastic because bakelite is not malleable. Bakelite is very hard. It's a network polymer, very large molecule formed, very rigid, electrically non-conductive, very heat resistant. So it was used, if you go down country roads and find power lines or telephone lines that have, actually power lines, that have been up for 2 or 3 decades, they might still have insulators sitting on top that are either discolored or maybe kind of whitish looking. They would be made of bakelite because they're non-conductive. Now, lots of times they use other types of polymers that are easier to manage. And some of the older ones, they even use glass. But bakelite is non-conductive, and therefore they can use it for that, isolating that conductor from the pole. Kitchenware used to have kitchenware that was made of Bakelite. Billiard balls. I think billiard balls are still made of Bakelite. Okay. So those are the essential types of polymers. But like I said earlier, this is not the end of the story. Once you've produced the polymer, your polymer may have side groups on it that give it a certain chemical and physical properties. But maybe you don't like those properties. So you can also go in and modify those side groups. In this case, we have polyvinyl acetate, PVA, which is commonly found in Elmer's glue. And if we chop off the acetate group, right, CH3CO acetate group, we're left with an alcohol, and that polyvinyl alcohol is actually water soluble. So that's what they use in these dishwashing and clothes washing pods with the detergent in them. They're perfectly stable as long as you don't get them wet. Right. So you'll notice if you reach into a box of dishwashing pods and you try to pull one out and it's sticky, it's stuck to one of the others. A little moisture got in there and caused them to dissolve into one another. So you have to pull them loose and hope that they don't burst when you do it. But when you put them in your washing machine, it hits it with that hot water, that just completely dissolves and releases the detergent. This is known as post-synthesis modification. And it always involves modifying side groups. Another possibility. We know that, well, actually, I think this is the mechanism for that modification. We know that vinyl alcohol will tautomerize to acetaldehyde. Yeah, ethanol is more stable. When you put the double bond on the oxygen, it's more stable than on the carbons with that oxygen withdrawing group. And then that's one example. Vinyl acetate. How does that work with vinyl acetate? Maybe it's next slide. Nope. Sorry. Okay, never mind. Polyether ether ketone. This polymer, we used to use this polymer in our high performance liquid chromatographs as a tubing for transferring materials. It's easily, the connections are very easy to make between two tubes, right? We've got the technology for that, and they're very stable, can withstand high pressures, so you can deliver your solutions at high pressures into the chromatograph using this tubing. So what we're saying is that if we, this is a side group. When we first form the polymer, we form it with this tertiary butyl group on the side, and that prevents crystallization. And then when we're ready to make something out of it, we remove that side group, and that makes polyether ether ketone. Once we remove that side group, it prevents crystallization primarily because it's steric hindrance. It doesn't allow the molecules to get close enough to interact in such a way that they will solidify into a solid crystal. So you can handle them. And then once you've got them where you want them to be, then you can remove the butyl group and they will assume the form that you give them. All right. I mentioned earlier the let's see, network polymerization and 7, right? Side group modification. Hey, this could be considered sort of a side group modification. And it happens when you get two polymers that you want to link together in some way. Say, in this case, we want polyvinyl alcohol, which dissolves in water, but we want to turn it into a solid. If we link multiple polymers together, that will form them into a clump and solidify them. And the example here is to use borax. Right? Borax will cross-link between the two molecules and convert them from liquid into a solid. I use this for demonstration with kids when they come through on tours. We get saturated borax, right? Just right off the shelf. Borax, 20 mule team borax off the shelf. And dissolve it in water until it's saturated. And then you put that in a tray, and then you have the students, I'll give them Elmer's glue, which is polyvinyl alcohol. And, well, actually, I think it's a mixture. It's either acetate or alcohol, one or the other. And you pour it in there, and you have them with their rubber hands, with their gloved hands. They start working that glue in that solution, and forms cross links. And then if you roll it up and make a nice ball on it and let it solidify, you make super balls. They like that demonstration. That's one form of cross linking. We can also cross link with formaldehyde, right? C2O is formaldehyde, and you can get that a similar cross linking between the polyvinyl alcohols. Natural rubber here. Remember I think we studied this earlier. Isoprene. Isoprene is that five-membered, branched, five-membered group. Let's see. 1, 2, 3, 4, 5. So that's isoprene. Polyisoprene is actually cis polyisoprene is natural rubber. And it's very gooey. It really doesn't make good tires. So vulcanization, which I think was produced by Goodrich, first by Goodrich. It was either Goodrich or Goodyear, one of the others. Learned how to cross-link the polymers with a sulfide bridge, polysulfide bridge between them. It can have 1 sulfur, 2 sulfurs, 3 sulfurs. Mostly, that's all they have. But this cross-linking stabilizes the rubber, the natural rubber, and makes it tougher. Right? It's got those covalent bonds between the molecules that stiffen it and make it tougher. So we can make tires out of it. All right, classifications. If we want to, let's see, side group cross-linking. Okay. If we want to classify polymers, these terms, these ways of classifying have been developed over years as being convenient. what type of main chain do you have? What are the functional groups in the main chain? What is the monomer that's used to make the polymer? How many of those monomers go into the polymer? And that can be a range. So let's see. This main chain here classified as purely carbons, only carbons in polystyrene. The main chain is a carbon chain, period, with side groups. Whereas this copolymer, nylon, has main chain with heteroatoms in it. In other words, it has periodic amide bonds. So we call those heterochain polymers versus carbon chain polymers. I imagine you could make polymers with non-carbon chains, right? Isn't that how we make silicone rubber? Right? Instead of carbon, we use silicone to form the polymer. Let's see. Functional groups, right? Functional groups and how the monomers are linked. Right? We can link them with ester linkages, amide linkages, ketone, ether linkages, various types. We can have the functional groups also. Functional groups can be identified and how they're linked. Well, I mentioned that already, how they're linked. There's a polyester as example. The repeating unit here has 2 ester groups in it for polyethylene terephthalate. The one on the left is complete, we say, because it's within the repeating unit. The one on the right is incomplete because it needs connection to the next repeating unit to be completed. Okay, we can identify the monomers, what goes in to the production of the polymers. And we can identify the repeating units and how many of them there are, the degree of polymerization. There are other terms that are used in the industry. If you buy a carpet, very often they'll say our carpets are polyolefins. That is, they're produced from monomers with only one functional group, and that functional group is the carbon-carbon double bond. That's a polyolefin. And then some of these carpets have a combination. They're a blend of polyolefins and nylons. The only reason they would use nylon is because polyolefins are very difficult to add dyes. You can't get them to give you good colors. You can get maybe grays, whites, obviously. But if you want colors, then nylon works better. Problem with that is they don't stand up to wear as much as well as with polyolefins. Then you can identify homopolymers, right? Polymers that are made of only one repeating unit or formed from only one monomer. Or copolymers, I've already mentioned these. because it was stream of consciousness. We could form this styrene butadiene rubber. So we have, excuse me, yeah, copolymers. Now they're trying to make a liar out of me. Each monomer is capable of undergoing self-polymerization. Then the resulting polymer is called a copolymer. Now the way it was taught to me was, you could have a heteropolymer with two monomers that can each individually form their own polymers under the right conditions. But when you put them together, they're well, I guess they wouldn't be copolymers then, because copolymers have the monomers cannot polymerize on their own, right? So I would have to argue with Dr. Carty on this one. Okay, I see what he's saying. They form homopolymers as separate entities, and when they're put together, they can form a copolymer. All right, that just makes things. Now, definitely, nylon is a copolymer. Why does it say it's not a copolymer? Well, if it's not a copolymer, what is it? All right. So I have a bone to pick with this slide and the person who wrote it. Nomenclature. All right, there are two ways to name compounds, just like always. There's the trivial way, or the common name, and then there is the IUPAC name. For polymers, IUPAC always uses the repeating unit. They say poly, whatever the repeating unit is. So in this case, polymethylene is the IUPAC name. But the common name would be based upon the monomer. Polyethylene would be the trivial name. But they're the same molecule. And then there are trademark names also. Um, if the name of the monomer consists of two or more words, then the name of the monomer appears in parentheses in the name of the polymer. So, for example, the monomer name here is tetrafluoroethylene. And when we polymerize it, we get polytetrafluoroethylene. That would be a trivial name. Actually, that would be the IUPAC name too, because look at the subunit here. Ethyl, tetrafluoroethylene, polytetrafluoroethylene. So in that case, both of them are correct. Both the IUPAC and the common name are the same, polytetrafluoroethylene. And if we have a methacrylate, that monomer has two words in it. We need to put those in parentheses so that we're not saying it's polymethyl and then methacrylate down the line. It's the monomer is methyl methacrylate, and it's a polymer of that molecule. Plexiglass. From a practical standpoint, plexiglass is great, but don't try to drill it, right? Unless you really know what you're doing. If you try to drill plexiglass, half the time it'll send a crack out. Whereas polycarbonate or Lexan, you can drill it all day long and it'll never crack. It's just something about the molecular structure. polyethylene terephthalate nomenclature. So here we have terephthalic acid, ethylene glycol, and this, the ethylene and terephthalate are together in this ester, and that's the poly form. So we put them together in a parentheses. Okay. Now, once we've got our polymer, we need to be able to characterize it. Like I said, if you're going to make a polymer and try to sell it to someone so they can make a product out of it, then you need to be able to characterize it in such a way that they know what they're getting and they know how it's going to behave when they try to manufacture. One of those characteristics is thermal transitions. The other is solubility. So those are two main characteristics of polymers. We can say, and this goes back to general chemistry, we can say a solid is either crystalline or amorphous. The main difference is crystalline solids have repeating units. You can identify repeating units in a crystalline solid. The arrangement is regular and repeating, whereas amorphous solids are just all over the place. There's no rhyme or reason to them. Now, as far as melting point goes, or transition point for temperature goes, crystalline solids have a reasonably well-defined melting point. My students do an experiment with benzoic acid and lauric acid. It's a colligative property thing where you want the melting point of melting point of lauric acid as the solvent, and the melting point of lauric acid plus benzoic acid as the mixture. And then the difference in those temperatures allow you to determine eventually the molar mass of benzoic acid. The problem is lauric acid doesn't form a crystalline solid. So its melting point is kind of in a range. And that's typical of amorphous organic compounds. Glass is a good example. Glass is an amorphous solid. In fact, some researchers like to call it a supercooled liquid. I don't know what difference that makes, but it's amorphous. So it goes through a transition. There's a transition temperature, a glass transition temperature, they call it, rather than a melting point. So TM for these, melting point, and this is glass transition temperature, which is really kind of the middle of the range for the temperature range at which it changes form from one to the other. And one way that we determine that is it loses mechanical strength. It's hard to tell when it goes from solid to liquid, but we can tell when it starts to get oozy. And it goes through a range, that temperature range. Now, if we have a polymer like high density polyethylene, where you can get the molecular chains laying one on top of each other, that's a crystalline structure, and high density polyethylene typically has a melting point. Whereas low density polyethylene, which has side chains and doesn't form that regular structure, has a glass transition temperature. And it's typically due to stronger intermolecular forces for the crystalline structure and lower entropy. Whereas the amorphous polymers have weaker intermolecular forces and higher entropy. Okay. These are just important values to report for your polymer. You need to know it because that tells you how the reaction proceeded, right? Did it end up where you wanted it to? That's your quality control, right? You check the glass transition temperature or the melting point, and that tells you if the reaction proceeded. If you were working in a manufacturing plant and you had this big reactor going, making polymer, and you take a sample of the product and you run it through your lab and you do this test and several other tests, then you can tell the operators, yeah, keep going or stop now before you waste more of your feedstock and fix the problem. If room temperature is above the glass transition point for any polymer, or we call it an elastomer, then that allows it to be more flexible. And that's why racket balls made out of this whatever type of rubber you want, neoprene or even natural rubber, then they will deform more readily if room temperature is above their glass transition point. The nice thing about some polymers is that they become plastic when they're heated, right? If you heat them above their glass transition point, then you can squirt them into a mold. And then when they cool down below their glass transition point, they resolidify. That's where the term plastic comes from. Thermoplastics. Let's see. Are they going to tell us thermoplastic? Let's see. Heat makes liquid. The other type is thermoset, and heat makes solid. Typically, thermoplastics, when you heat them and they get liquid, you can inject them into a mold and then they resolidify. Thermosets, though, when you heat them up, they form extra linkages, and once they're set, they don't go back. All right, certain types of intermolecular reactions. We can use this where we have the carbon chain, homopolymer chain of carbons, and then we have different side groups. We'll modify the glass transition or melting point temperature. All right, so if we have polypropylene with a methyl group on the side, it has a very low glass transition temperature. But if we add a more electronegative atom on there, like chlorine, we increase that temperature. If we change it to an acid group, we increase the temperature further. And if we ionize that group with, say, strong sodium, like sodium hydroxide, then we can increase the glass transition point up to a point until we reach a point where it starts to decompose, right? There's a limit. If you heat it up too much, then you're going to start breaking bonds in the molecule. Okay, branching. Polymers that are more branched tend to have lower melting points and glass transition temperatures. Polymers with longer pendant groups, side groups, also have lower glass transition temperatures or melting points. Now let's go back to the tacticity concept. Isotactic polypropylene has a very regular structure. All right. Notice those methyl groups are all on the same side. All the same stereochemistry at each one of those carbons. Has a very well-defined melting point that is well above room temperature. Atactic polypropylene, where the methyl groups can go any which way. There's no regularity to them. They get tacky at room temperature, and they have a wider range glass transition temperature. Okay, here we're comparing polyether ether ketone and against polyethylene terephthalate. Notice the difference in melting points. Polyether ether ketone has 365 degree, much higher temperature, and that's one of the other reasons we use it in the lab. And then polyethylene terephthalate has a lower temperature, but it's still very strong. Don't get me wrong. I use those bottles for my I pressurize them for a Boyle's Law experiment. Right, they'll stand up to 100 psi at least a couple of times. Okay, we're looking for regularity. Regularity in the positions of these polymers atoms is influenced by the rigidity of the polymer chain. So polyether ether ketone is more rigid than polyethylene terephthalate, much more rigid. The more rigid the polymer, the fewer the possible conformations of the polymer, and the greater the likelihood that the polymer will achieve regularity in the positions of its atoms. Polymers that are rigid tend to have higher melting points or glass transition temperatures than do polymers with flexible chains. And we pointed out the flexible part of the molecule, right? This ethyl group right here is the flexible part. It can bend and twist. One of the reasons that the polyether ether ketone is rigid is because its chain is conjugated. Right? Notice that. Right? We've got p orbitals and alternating, in many cases, alternating pi bonds with single bonds. Then when you get to the oxygen, it has available p orbitals there that can conjugate with either side. And when we get to the carbon, it's got oxygen there with available p orbitals, and we can further conjugate. Whereas with polyether terephthalate, polyethylene terephthalate, this ethyl group breaks the possibility for conjugation. Right? So that conjugation adds rigidity. All right. What else can we say about these pendant groups? If we look at it in this Newman projection, right, we see that for a polyethylene, that the regular chain length is going to be zigzag, and the ends of the chain at any one of the two carbons, ends of the chains are going to be anti to one another. And that's ideal. But if we add a bulk to it, right, like this methyl group for polypropylene, then the more bulky parts of the molecules are going to be the long chains. Like if we start at one, we're looking at this one here, then we're going to have that, and then that, and that, and that, this, and this, and this. Well, if we're looking down this chain right here, these long chains are the ones that are going to have to be anti to one another because they're so big. So the methyl group that we add is going to be on neighboring carbons. Well, we're going to have a methyl group here and a methyl group here. Oops, wrong side. So every other carbon is going to have a methyl group on it. And if we look at the way that they're arranged, those methyl groups have no choice. They have to be syn. They have to be syn to each other, right? Because these parts of the molecules are so big, they win. They cannot be syn to one another. They have to be anti. So what that does is that makes the rotation less likely. You can't rotate around that bond. It adds to the rigidity due to steric strain. All right. Now, that was temperature, characterizing polymer by temperature. How about solubility? When the intermolecular interactions involving the solvent molecules are similar to those involving the polymer molecules, the polymer tends to dissolve. So what does that mean? That means if your polymer has, if your solvent is, say, water, right? It has the potential for hydrogen bonding, or at least dipole-dipole interaction. And your polymer has lots of potential for hydrogen bonding on it, then it's definitely going into solution. Like polyvinyl alcohol, it's extremely soluble. Other polymers, natural polymers like starch, right? Starch is a polymer of glucose molecules, and it's just covered in alcohol groups. So that's why you can get starch, you can get sucrose, which is only a dimer of fructose and glucose, but you can get a lot of that into solution because of that hydrogen bonding potential. If you try to put starch in, say, I don't know, vegetable oil, it won't go, right? It just will not go because the interactions are not there. Okay, so polystyrene dissolves in toluene, right? Like dissolves like. Nonpolar dissolves nonpolar. Polyvinyl alcohol dissolves in water. Polar dissolves polar. Ionic side groups will dissolve readily in water. Now, if you have cross-linking in your molecule, that tends to limit the interaction between solvent molecules and the polymer, which decreases their solubility. So if we have polyvinyl alcohol in Elmer's glue, and we put borax solution in it, then it's in solution first, right? The polyvinyl alcohol, it's kind of thick, but it's still in solution. Then we start cross-linking it, and it forms a solid. We make superballs out of it. It's no longer soluble. Crystalline polymers have lower solubilities. They tend to have strong polymer-polymer interactions, making it difficult to establish the polymer-solvent interactions. All right. Let's see. Polymers are good choices for some food storage, right? Some of them are, because they're both insoluble and impermeable to water, and they don't pass air, and they're relatively inert. So we don't want them to react with our food, right? Contaminating our food, and we don't want to eat that stuff. And because certain polymers, polyolefins in this case, are insoluble, then they make good plastic wraps or plastic containers. Three different densities for polyethylene. I mentioned low density and high density. There's also linear low density. And here are your different glass transition temperatures. All right, so polyethylene, high density polyethylene, which makes good container for milk. You know, I don't remember talking about the Ziegler-Natta catalyst. Maybe, yeah, I think we did. We did. I just kind of breezed past it. The low density and high density polyethylene is synthesized using this Ziegler-Natta catalyst that prevents branching. Because of its increased crystallinity, high density polyethylene has a higher melting point and higher tensile strength. We didn't mention that one. Tensile strength just means how hard can you pull it before it breaks. This makes high density polyethylene suitable for applications where low density would fail, such as milk jugs and other liquid containers. Low density polyethylene and polystyrene have lots of branching, right, or side groups. Right? So they're good for well, okay. Linear low-density polyethylene is made by copolymerizing with ethylene and small percentages of alkenes and but1-ene. So it's technically not linear it's not low-density polyethylene because we're incorporating other molecules into it. But we can increase the strength while maintaining some of the flexibility, right? Because these garbage bags, they need to stretch without breaking, right? So we allow them to stretch and absorb some of that energy in moving the molecules apart. But once you reach a certain point, then they will eventually break. All right. How about polystyrene is not flexible, right? And that's largely due to that side group, right? That phenyl side group makes the polystyrene more rigid. All right. So we make rigid products out of it, right? I think one of those is a disposable razor, and the other one is a insulated polystyrene container, right? You know how these polystyrene containers are made. Polystyrene is made with gas injection of some kind into the matrix. So it inflates them and they make beads out of them, little beads. So when the manufacturers want to make these things, they heat them up slightly, not enough to melt them, just enough to where they'll stick. Then they injection mold them into these. Right. Well, we use some of them in the lab, right? And if you look at them really close, or you break a piece off, you see these little beads, right? They're just stuck together, and they have closed cells inside, so which does not allow water to pass through them, but it creates gas pockets and that makes them insulators. Here's PET, right? What happens when you injection mold it, right? Put it under pressure, you stretch it into the mold, and what it does is it causes tension on the molecules and unidirectional stretching, right? And that makes it more rigid. So the manufacturing process modifies the physical behavior of a polymer. All right. So these PET is very good. It's very low gas permeability. It's very inert. It's extremely strong, so it can hold the pressure of carbonated beverages. But relatively high, well, tensile strength means it's strong. It has 4 times the tensile strength of high density polyethylene and twice the strength of polystyrene. Now, one thing that we haven't talked about is chemical compatibility. If you get into a lab and you need to store chemicals separate from their original containers, or you mix up a concoction and you need to store it, you need to research the chemical compatibility of the polymer, the bottle that you're going to use. If it's not glass, then the polymer you're going to use as your container, and how will it react with the stuff you want to put in it, right? Some of them don't like chlorinated solvents. Some of them don't like high pH. Some of them don't like strong acids. All right, so the only way to do that is to go to a chart with chemical compatibilities, and several of manufacturers put those out. You can find them anywhere on the internet, or in some of them actually are in. I know there's one in Cole Parmer catalog, right at the very back. They give you compatibility of polymers, so you'll know that your container will not disintegrate over time based upon what you put in it. Now, if we're going to recycle things, that's what this recycle triangle is for. I mentioned 1 first, that's polyethylene terephthalate. 2 is high density polyethylene. 3 is polyvinyl chloride. And 4 is polyethylene low density. 5 is polypropylene. 6 is polystyrene. And the rest of them don't have numbers. If it's a 7, it could be anything. It could be nylon, polycarbonate, polyacrylic. It could be anything. And they put the they bunch these 7s together because they're so difficult to recycle. So if it's got a 2nd on it, they probably sort it out and throw it away. All right. So how do we recycle plastics? Well, first of all, you got to be sure they're clean. Right? So plastics that's been used for needs to be graded, sorted and graded before you try to incorporate it into some sort of manufacture. You can also degrade it, right? This polyethylene terephthalate, if we hit it with acidic alcohol of some kind, we can break the bond, break the ester linkage, and form the ethylene glycol and the diester again before we reuse it. So that's chemical recycling. Mechanical recycling, you simply just take the whole plastic intact and make something new out of it. Usually, poly sets won't work, right? Because they're fixed. If you can't do anything chemically with them, they have to be discarded. But thermoplastics, you can heat them and remold them. Chemical recycling, you degrade the polymer into its subunits and then regenerate the polymer however you want. Biodegradable plastics. Very few of the polymers we make are biodegradables. They sometimes they will degrade under the influence of ultraviolet light. Right? Sometimes we need a catalyst to make them degrade. Polyesters, polyamides, polyethers, they tend to be biodegradable. And most polymers that we make now are not renewable, unfortunately. There's still work being done, of course, being produced from renewable resources like, well, our example here is corn. And I'm reminded of a class I took in soil microbiology, where we were learning about how things degrade, like a tree falls in the woods. Right? Maybe somebody heard it, maybe somebody didn't. But once it falls, what happens to it? Right? You come back several years and it's started to break down. Right? So what happens? Well, of course, the first degradation process is mechanical. Right? You get bugs going in there and eating the cellulose, right? Digesting the cellulose because they have the microorganisms that can do that. So it's a mechanical degradation. They break it apart into smaller pieces. And then, of course, woodpeckers come along and they hammer away and they eat the bugs. But it's mechanical to start with. And then once you can get water and microorganisms, molds, fungi, bacteria, into the wood, then they will start to break it down also. But the first thing that they go for are the side groups. These polymers will have side groups, and they'll go for those, and they'll break them apart, and then they'll break apart sigma and double bonds fairly easily. The ones that they go last are the aromatics, right? We learned that aromatics are extremely stable molecules, and it takes a special enzyme system to break them apart. They're the last things to go. So when we throw something out into the environment, the first things that are going to go are the side groups. Right? They're the easiest to break. The more reactive parts of the molecule will typically break first. And some polymers are extremely stable. They don't break down easily. So as our last topic, we'll say a little bit about biological polymers. And those can come in various forms. Proteins, I mentioned earlier, those are amide linkages between amino acids. Carbohydrates are polymers of various types of sugars, usually. Not always, but most of them are sugars. So we form starch, right? Plant starch is essentially a linear polymer of glucose. Animal starch or glycogen is a highly branched version of glucose polymer. Cellulose is another type of glucose polymer that has the glucose molecules turned a certain way so that enzymes can't break them apart. Most enzymes can't. Takes a special kind. So those are carbohydrates. And the carbohydrates aren't always polymers, right? They can be simple sugars too. But the polymers that are formed from simple sugars are included in carbohydrates. Nucleic acids. Nucleic acids are polymers like DNA, RNA, are polymers of nucleotides. And they're all constructed from small building blocks. Let's see. Mentioned those already. So here's when we talk about proteins as a, let's see, let me erase some of this. Proteins as a polymer. Proteins function as polymers, but they're very specific in the way that they are made and the reactions in which they participate. That's how the cells control reactions. And we look at the structure of proteins at actually 4 different levels, right? The primary structure is simply the sequence of amino acids, just how they're hooked together with their amide bonds, their peptide bonds. So amino acids linked in this straight chain, they can branch too, but most often they're straight chains. This is the primary structure, simply the sequence of amino acids. Now we can get some cross-linking. You can cross-link, especially 2 cysteine amino acids, cross-link to form a cysteine product. And that's used in further structures past the primary. Secondary structures are the way the molecule interacts with itself. Since it's a long molecule, right, it can turn back on itself, or with its neighbors. And these come in 2 basic forms. The alpha helix, which is just what it says. The molecule just forms a helix like this, or the beta pleated sheet. And this gives molecules, proteins, chemical and physical properties that are unique. And these 2 types of secondary structure can occur in the same molecule, right? Part of it can be alpha helix, and then it switches over to beta pleated sheet. So it doesn't have to be one or the other. Now, one thing about the alpha helix is it's kind of like a slinky, right? It's flexible. It can move like this, limited amount. Beta pleated sheet is very rigid, right? And very strong, because the molecules are lined up with one another. They can interact, right? Form their intermolecular bonds. And you will find beta pleated sheet and alpha helix in spider silk, right? The sticky spider silk and the stretchy part of the web is going to be alpha helix. But the very strong silk is formed into beta pleated sheets. Right, so you can, once you've captured your prey, you can wrap them up in a beta pleated sheet and they're not getting out. You hold on to them till later when you suck the body fluids out. Then there's tertiary structure. Tertiary structure is folding of a molecule. So, and typically what happens is it depends on the environment. Let's say the environment is in a cell, so it's primarily aqueous, right? Hate it when this happens. Typically polar. So the molecule may fold itself so that the polar parts of the molecule, the amino acids that are particularly polar, are facing out, and the nonpolars are facing in. Okay, that's one of the reasons that it would do that. The other reason is the structure, the folding, the tertiary structure of the protein allows it to function as a catalyst, an enzyme. By that folding, we create pockets, and it lends itself to what's called the lock and key mechanism for enzyme function. In other words, the substrates that come to that enzyme, if they don't fit into the lock portion properly, then they won't react. Right? So that's how it's very specific in its reaction. This is based upon the tertiary structure, and it can be extremely complicated, complex. And this is also one way that enzyme activity is controlled. Right? The signals are sent into the cell that cause the conformation, the tertiary structure of an enzyme to change from its inactive state to an active state. And then it catalyzes certain reactions until the signal is sent for it to revert back. Let's see. Quaternary structure. Okay. Quaternary structure. Tertiary structure is single molecule. Quaternary structure is multiple molecules. How does two or more molecules fit together to perform a function? Right? Tertiary structure may not be enough. Perfect example of this is hemoglobin. Right? Hemoglobin has 4 chains, 2 alpha chains, 2 beta chains. And within each chain is a heme group. A heme group is like a cyclic cloth function that holds iron in the middle. Right? It holds that iron in there so that the iron is stabilized and it can attract oxygen. So these 4 chains come together in a certain way in this quaternary structure to accomplish their mission. Another one is this aspartate carbamyl transferase. It's an enzyme. Now, some enzymes won't function at this level. They have to be combined with several molecules to produce its functionality. Okay. Polysaccharides. Saccharide means sugar. These are polysugars. Polysaccharide. Amylose is a starch. It's an unbranched polymer of glucose. Makes up about 20% of starch. That is, it's a storage polysaccharide. Right? If you go to biochemistry and you're going to learn about energy movements as controlling the types of reactions that occur, right? Energy demand, energy input. And one of the ways that cells survive or organisms survive, is to store energy during times of plenty. In, say, starches is one way to do it. The starches are readily available. They can be broken down quickly and the energy produced quickly, right? Unlike fats, right? Fats are long-term storage. Polysaccharides are short-term storage. And it forms this helical structure, right? It's kind of like proteins in that way, right? It forms a helical structure. This is now we don't speak of polysaccharides as primary, secondary, tertiary structure. That's for proteins. But it can form this helical structure, and it has extensive hydrogen bonding. Makes it very in water, because look at all those alcohol groups, perfect, and oxygens, perfect places to form hydrogen bonds. So starch is typically very soluble in water. Let's see. Amylose is unbranched, all right? Polysaccharide and amylopectin is about the other 80%, and it's branched. Right? It forms a branch at the number 6 carbon, a 1,6 glycosidic, and this is these are these terms that you're going to learn if you get into biochemistry. The glycoside bond, the alpha 1,4 glycoside bond in the linear chain is starch. The beta 1,4, which flips the oxygen the other way, is for cellulose, and that makes it unapproachable by most enzymes, which stabilizes it for structural purposes for plants. Plants also make starches, right? And those are readily available for energy. All right. Here we go. Cellulose is a 1,4 beta linkage, and it's not broken down readily by most enzyme systems. So it's essentially a structural molecule. It also adds potential for hydrogen bonding within the molecule, which makes it more rigid. All right. We could have talked about other things like DNA, RNA as polymers, but you're going to get a snoot full of that. If you get into biochemistry, you'll get enough of that.